Let's go through the code 1902 depth of binary search tree given insertion order. It gives us an integer order. The number in this array are permutation from 1 to n, which represent the order of insertion into a binary search tree. For example, this order equals 2, 1, 4, 3. And that means we insert the root as 2, then left child 1, and 2 is right child 4, and 3 uh, will be the left child of 4. And let's return the depth of the binary search tree. The depth is defined as the longest path length. For example, 2, 4, 3. It has the longest path. So it is the length is actually not the age, it is the nodes. How many nodes it is? For example, there are 3 nodes, so it is return 3. So for this question, we are going to do in two methods. One is we are going to doing the forward direction, which we insert node by node, and in the end we find the longest path. And another is we do a reverse order, and which we from its child tree and find its root. And forward direction, we are going to use the tree map, and reverse direction, we are going to use the union find to do this. Um, so let's look at first. Let's look at when we insert a value v to our existing binary search tree. The insertion path is actually completely determined by comparison. I say, for example, let's look at this v equals, if it equals 3, right? You will see there's no other place to insert. Um, and also for the other nodes, right? So how can we find where should we insert these 3, right? So consider when we insert, we already insert some other numbers. So our strategy is that we find this V's preprocessor and also its successor, right? So how can we find this one's predecessor? So intuitively, what we think of, we use a tree set or tree map, those kind of data structure, right? So if 3, we find its flow key and ceiling, right? So the flow will be 2 and the ceiling will be 4. So let's look at the original, what we already have, the previous tree already have, right? So this is 2, 4. We find this and this, right? But the thing is that there is one thing is that these 2 and 4 they must be connected. Why? If if it's not connected, for example, if we have um, a structure like this one, right? That means between 2 and 4, they must have some values in it. But before insert 3, right? We have a ceiling key to be 4 and a floor key to be 2. That means there is no data, no nodes between 2 and 4 before we insert 3. Otherwise, um, otherwise we cannot find just 3 ceiling to be 2 and 4, right? So that means 2 and 4, they are before we insert 3. There is no data between this. But this kind of data structure means there is data between this. So it's impossible. So the 2 and 4, they must be connected, right? So 2 and 4, they must be connected. It can be 2, 4, can be 2, be leaf and 4 be the parent, right? So while we should we insert 3. Insert 3, we just compare which one has the longest path so far already, right? So either this one path has be this path plus 1, or this path is this path plus 1, right? So we just so what when we insert, we just insert the 3 to the longer one. So that will be our strategy. So let's write code for this. So we're going to have int n equals order dot length, right? So we have result equals to, we set a 1, right? Because it say this order is not empty. Should length this n at least be 1, right? As we talked about, we can use the tree map for the forward direction. The system map equals unit tree map. And we'll put root. The first one is root, order 0. And one thing to remember is that why we need a tree map is that we there are two functionality. One is we find when we insert V, right, we can find its flow and selling quickly. Another is that we need to store its longest path already, right? So the value will be the longest path for this node. So what we do is for int I equals 1, I smaller than int I plus plus. So we're going to have int v equals, this is the value we're going to insert, order I. And we're going to have map dot entry integer. Let's call it N1, N2, right? Because we don't know which one will be the parent, but we know N1 and N2, they must be connected. Because before insertion, before insert the V, right? There is no data between this N1 and N2. So will be map dot flow entry V, and N2 will be map dot selling entry V. So we're going to have a int d1 equals n1 equals null. If it is null, then that is will be 0. Otherwise, will be n1 get value, right? And d2 equals n2 equals null. If it is null, it will be 0. Otherwise, it will be n2 get value. So current our insertion for this V, right? Our D will be max D1 or D2, right? So we'll see actually D1 and D2, they just have one. If they both exist, it will be just one differences, right? And there is another scenario is that can we let's try to see, is it possible that it is possible another one, it is 0, right? Because we don't have a selling. For example, we are insert 5, there is no 6, right? So that is possible as well, right? And if they exist, then you just plot one, right? So this will be our kernel depth. So our result will be mass every time we insert, we just compare our result with D, right? And also we need to put uh map put this VD. In the end, just return result. So this is the forward direction solution for this, right? But doing like this, let's look at the time. It is not that good, right? Because the reason it is because the time complexity was it is a tree set data structure, right? So the time complexity every time we insert will be a log operation, right? So averagely, we'll say there are it is n so um we'll say it is a log operation. So totally we'll say it is an n log n time complexity and with O n space complexity. So we'll see the performance may not be that good. So let's look at it whether we have some other approaches. Um, so instead of build the tree in a forward direction, um, we can also consider this order in backwards or say delete order. Um, so what we do is that a moment ago we set, for example, the root depth is 1, right? Keeping adding, this is will be 2, this will be 2, and this will be 3, right? And now what we do is that we from the leaf, we'll say this is 1. So if we see a node, this depth will be 1. And we are keeping, so this is the first node we see, right? We know this must be a leaf. And then we see 4. So how can we handle 4, right? So we know 4 will be 3's parents. So how do we know? Here, intuitively, we know 4 is 3's parents. 3 will be 4's child. Um, so let's look at the step first. So we know this we're going to add this depth to be 2, right? And 1, let's go to 1, right? 1 does not have child. Let's set it has pass as 1, right? And let's go to 2, right? 2 has 2 child. One is 1 and another is 4. And for this 4, it has depth 2. So what will be these roots pass? It will be max 1 and 2. Then plus 1 will be 3, right? So now we are doing like this kind of order. So when we insert a node, we'll see we are not inserting, actually we are deleting, right? So when we iterate to a node, what we thinking about is that for example, we have a node V. We look at its child just in the V's here, right? So the child must be somewhere in this part, right? Somewhere in this part, it may be two subsets, right? One of its left, one will be its right child. So if we insert a V here, so iterate to a V, right? And we already have its left and the right. So its depth will be max its left depth plus and left its of its right depth plus one, right? So this will be its new depth. Um, so here, we from its child to its parents, we'll see this is a connection problem, right? So how can we handle connection problem? We intuitively want to think about is use a data structure called union find. So union find, sometimes we can have we need of course we need the father's array or map, right? And also we need a height array. Sometimes we can put this array into union find data structure. Um, and here the things that for union find for this question, we are just use this one to connect the nodes. For example, we are have a v, right? We know v plus one. If it already exists, it must be on its right child tree, right? Can be somewhere in the here, right? And if v minus one, if already exists, it must be in its left child tree, right? Can be somewhere here, or or even v minus one here, right? This is v minus two error, or this is v minus two, this is v minus one, right? So it must be in. So v minus one, if it already exists, that means we already have it from the reverse order. Then it must be in its left child. And if v plus one, if already exists, then it must be in the right child. So what we do is that we don't know if this v minus one, if it is exactly its left child or not, right? So how can we do to handle the depth? We can use union find this v1's parents, right? So this is the parent. This parent or um, or root parent, right? Grade parent will always be this v's left child, and this v plus one's grandchild parent will always be its right child. So this is the essential thing what we need to do, right? No matter whether this is v minus plus one, it is root or not. It may not be the root. It may be a leaf, but the thing is that its grandparent must be this v's right child, and also we use a height array, right? Height array to store those kind of nodes heights, right? So even this v plus one is heights. For example, this is a leaf, so the height is one, right? It doesn't matter. We find its grandparents' heights. That will be this tree's height. So this will be the concept. But for union find, we know there are two types of implementations. One is using map union. We something like we use union find, use a map, right? Something plus union find. We can use a map integer, integer, and father was new hash, something like this, right? So The advantage of using a map is that we don't need to initialize every element in advance. So if a key doesn't exist, we can simply add it dynamically, right? So for this for so actually for this kind of question, use map will be will be uh, kind of straightforward, right? But use array, the advantage is that this is a number, right? Array will of course be much faster. And because the index is simpler, more efficient. Um, the disadvantage use arrays is that it's a bit confusing is that since it's not always clear whether a particular node is already initialized or processed or not, right? So what we're thinking about is that for this union find, we use integer array, but we don't write the union method. We just write the find method. And for the union, we union it in our own logic. And we also do not put the hate array in the union find. So what we do, let's write code for this. So we're going to have an int array father, and we are going to public union find int n. So for, we'll say father equals new int n, right? And for int I equals 0, I smaller than int I plus plus, other I equals I. And we can write the find, right? Int. Find is do the test compression. So if x equals father, x, just return x. And here we are going to have recursion father x equals find father x, return father x, right? So this will be the union find have a class. And we want to use, we know we put the heights outside the union find because the thing that if we iterate a node, we'll set this height at least to be 1, right? If it is 0, means we didn't see this node at before, right? So what we do is that we're going to have int n equals orders dot length, and we are going to have height equals new int, because it need a n, right? So at least n plus 1. But we are going to use this n plus 2, right? Because the things that for every node, we treat the age will also similar. That because for every v, right, we insert, we want to see v plus minus 1 and v plus 1, right? So if v happen to the n plus 1, the node n, right? Then we need the n plus 1 with it exists or not, right? So let's set this to be n plus 2. And then we are going to have a union find UF equals new union find. And we're going to have result equals 0, right? Of course, we can set as 1, right? So what we do is that for int I equals n minus 1, I greater equal to 0, I minus minus. So we'll see int v equals height uh, order I. So so we are going to have int f1 equals uf find v minus 1, right? And f2 equals uf dot find v plus 1, right? So we know this is v, right? V minus 1, v, this is v plus 1, right? So we need to find this. So let's see if height f1 is greater than 0, right? That means we already have this. So that means this f1, this is v, right? F1 must appears in the later part already, right? So if this is greater than 0, then we can connect, right? UF dot father f1 equals v, and we'll write if height f2 is greater than 0. So this is we do the connection is like a union, right? So um so we know our height v will be height max dot max height f1 height f2 plus 1, right? So even this is 0, right? We set this one to be 1. That means otherwise, so doing like this, for those nodes we already iterate, they will have at least height 1, right? So this will be a trick that for the interarray, for those kind of things, we dynamically initiate that as 1, right? So we just write our own union logic. So our result will be max dot max. So actually, we don't need the result with max. In the end, we just need to return height order 0, right? So let's have this be in part 2. So this is much faster because it is a ON operation with ON space, ON time complexity with ON space complexity, right? Okay, let's also have a Python implementation. I'm not implement the tree map, just keep simplify. I'm going to implement the union find operation method. solution. Okay. Union find it. And so we're going to have n result equals length of order and result to be 0. We can set it to be 1 as well, right? In the height equals this one multiplied by n plus 2 and UF equals union and n plus 2. So we are doing in a reverse order for I in range n minus 1 minus 1 minus 1. So V equals order of F1 F2 equals UF dot find V minus 1 UF find V plus 1, right? So if height, so we use this height. If you already greater than 0 means it's we already iterate it, right? Visit it. So UF fag F1 plus V, and we'll write if height F2 greater than 0, then UF dot fag F2 equals V. And we're going to have height V equals max height F1 height F2 pattern. In the end, result return height order 0. Mm, takes no argument. Union find takes UF takes no argument. N plus 2 has n as integer. Union find n plus 2. What's the problem? This should be on 2.